So earlier we have seen gravity dams and earthen dams, and in connection to the dams, we are going to see types of spillways, and then the energy dissipation below a spillway. Now, a spillway is a structure that is embedded into the dam to safely discharge the water. So if we have a reservoir and a dam, let's say this is the gravity dam. And if there is a flood event, then the water level would be rising. So at some point, the water will start to overflow on top of the dam. Now, we do not want the water to overflow on top of the dam. So now what we do is we construct a spillway on the downstream so that the water can be discharged through the spillway. So spillway is a structure provided to safely discharge water. Now, there are different types of these spillways that we are going to see. So the first is vertical drop spillway. So the vertical drop spillway is like the simple design of the spillway. Let's say this is our weir, which has more or less vertical face on the upstream and more or less vertical face on the downstream. Then whatever the flow is coming is going to go on top of this weir like this. So just a drop on the downstream side. We are not providing any streamlined structure. Now, because of this vertical drop, you see the flow is getting separated from the weir, and then you have some aeration or air trapped in this place. Now, the flow sometimes can be circulating as it flows down, and then what it will start is slowly move towards the upstream phase, and it can erode the the downstream phase of the dam. So there is a problem of aeration or cavitation in this. And the second is auger spillway or overflow spillway. So in this, what we would do is, let's say this is our upstream phase. For the downstream, we provide a curved surface. So let's say this is a low height dam. So for this, we have provided a curved surface. So now if there is overflow, that is going to follow the downstream phase. So essentially, we are eliminating the cavitation. This is auger spillway. Now, generally, the auger spillway is designed like a parabola, and the equation for this auger spillway, let's say this is my downstream phase of the spillway. Then this curved surface is given by an equation. So that is xn equals to k hd power n minus 1 into y. So let's say this is the flow that is overflowing on top of the spillway, and hd is the head on top of the dam, and x and y are distance. So x is in the horizontal and y is the vertical. So this surface you can find out by using this equation. And in this equation, there are two values which are k and n. These are constants. And these depend on slope of upstream phase. So the values of k and n depend on the slope of this upstream phase. So this is our upstream phase. Now let me show you an example of auger spillway, which you might have seen in most of the dams. So this is what it looks like. So you have a curved surface on the downstream. So the water is flowing along the curved surface. And then there are sluice gates. You see there are sluice gates on the top. Or you can call them spillway gates, either sluice gates or spillway gates. And after this overflow spillway, what we have is a chute spillway. So let us say I'm looking at the dam from the top. So this is my plan view. Let's say this is a mountain here, and then a mountain. So this is the reservoir, and this is downstream. And this is the dam. Now a chute spillway is, instead of providing spillway all across the dam, if I just provide a spillway in one particular section. So let's say I am providing spillway here. Then this is called chute spillway. So for auger spillway, you would provide spillways all across the dam. So you would have multiple sections of spillway. Whereas for a chute spillway, it's only provided on one side. Now the reason for this depends on the site conditions. So for example, if there are any adverse conditions like soil conditions or foundation conditions that would impact the design of the dam, then we would provide the spillway only on one side, not all across the dam. And you can see an example of chute spillway here. So it's just one spillway. Instead of all over the dam, you're just providing one single spillway. So this is chute spillway. Now, after chute spillway, what we have is a shaft spillway. So let's say again, I have a dam which is bound by mountain on both sides. And then this is the downstream, and this is reservoir. Now, you provide a shaft here. So the water from the reservoir is going to drain through this shaft. And then this shaft is going to pass through the dam, and then it would discharge the water. So if I draw the cross section, this is what the dam cross section is like. And then you provide a chute spillway, a shaft spillway that goes through the dam. So let's say this is the reservoir level, then the water is going to drain into this shaft, and from this shaft the water will be discharged onto the downstream phase, on the downstream of the dam. And this is what a shaft spillway looks like. So you can see the water is being drained into the reservoir. So, or even this example, you can see the water will be drained through the shaft and then it will be released on the other side. Now, if you go onto YouTube, you can find nowadays there are videos from vloggers who send drones through these shafts, and you can see how far the shafts can go under the dam. And then the last type of spillway is siphon spillway. So siphon, you might have learned about siphon action, right? So let's say I have a tank and then you insert a pipe. So if you remove the air in the pipe, then you are creating vacuum. So because of this pressure difference, the water is going to flow through the pipe. So this is siphoning action, right? Now we are going to make use of that principle in discharging water from one side of the dam to the other side. So let's say this is the dam. Now the spillway will be provided inside the dam like a shaft. So it is provided like a shaft. Now once you, let's say, prime this spillway with water, then water will start flowing. So once we remove the air, or once we create a vacuum in the siphon, then the water from upstream reservoir will start flowing to the downstream. So this is based on the siphon action. So these are the different types of spillways. Now the discharge over a spillway, we are going to see how to calculate the discharge over a spillway. So let's say I have a dam, a small height dam or low height dam, which is 10 meters or 20 meters. So this is the dam. And then let's say my upstream water level is like this, and the water is flowing down. So the height of the dam, I would say, is h, and the head on top of the dam is hd. Now you know there are two types of heads in water in open channel flows. One is hydraulic head, which is the depth, flow depth, and then velocity head, so which is generally given by v square over 2g, and here I'm calling it as, let's say, ha. So you might remember this from the specific energy. So specific energy is given by sum of hydraulic head plus velocity head. So y plus v square over 2g. You might remember this. So y is hd, and then v square over 2g is ha. So now if I want to plot ha, that would be on top of hd, and this is the total energy line. So from open channel flows, you might remember there is a hydraulic energy line and then total energy line. So the total energy line is flow depth plus velocity head plus the elevation. Now, the discharge over a spillway is dependent on this specific energy. So the discharge Q is a function of CL h power 3 by 2. So C is a coefficient of discharge, and L is the length of spillway crest. So let's say this is an effective length of spillway crest, then L would be the length. And H equals to HD plus HA. So it is the sum of hydraulic head and the velocity head. So if you measure what is the hydraulic head, and then if you also know the velocity in the flow, then you calculate what is HA. So based on the head on top of the crest, you can calculate what is the discharge the spillway can deliver. Now, when you want to design a spillway, you also need to consider this discharge capacity. So if the actual discharge is higher than the discharge the spillway can deliver, then the spillway can get damaged because of the higher forces. Now, after looking at the discharge, we are going to see at energy dissipation. So energy dissipators below a spillway. And why do we need to dissipate this energy? So does anyone want to take a guess why we want to dissipate the energy?
To reduce the erosion caused by.
Yes,
Okay.
yes, that's right. So if we do not reduce the energy, then the downstream material is going to be eroded. So to avoid that, we need to reduce the energy. And there are different types of energy dissipation mechanisms that we can use. And the basic principle is that we want to create a hydraulic jump. So let's say this is a dam and we have overflow. Now this is going to be a high velocity flow, and this high velocity flow is generally supercritical regime, and this has a tendency to erode bed materials. So to avoid that erosion, we need to dissipate the energy, and to dissipate the energy, essentially we need to create a hydraulic jump. So hydraulic jump, what does it do? So you have supercritical flow and you have subcritical flow. Through the hydraulic jump, you lose energy. So you might remember the equation for delta H, which is a function of depths y1 and y2, conjugate depths. Now to create the hydraulic jump, it may or may not be feasible all the time. So let's say if the bed is just horizontal, then we don't know if the flow depth is going to be y2 for the depth to happen, for the jump to happen. So we need to ensure that the flow depth is sufficient so that with the depth coming in with y1 can form a hydraulic jump. So to create a hydraulic jump, what we can do is to create stilling basins or buckets. So in a stilling basin, this is our spillway profile. So you extend it with an apron, and then so we are providing a raised section at the downstream end. So essentially you are creating a pool of water here with this raised section, and with this pool of water, then the supercritical flow coming in will start to form a jump. So this is stilling basin. Or you could just simply provide a sloping apron. So let's say if this is the original sloping profile that I had to provide, what I will do is to slope the spillway downstream phase like this. So this was the original, the dotted line was the original parabola or curved surface. Now instead of the parabola or curved surface, I have provided a slope. Now again, using this slope and an apron, you can create a pool of water that will also create a jump. So that is sloping apron. And then what we could also do is to provide a bucket. So this is what the dam is going to look like. So you have provided a curved surface here, like a bucket. So whatever the flow is coming in is going to roll and then go out. So the flow is coming in as supercritical. It is going to start rolling in the bucket and then go out. So with this rolling action, we are losing the energy. So this is called a roller bucket. And the last dissipation mechanism on the spillway is similar to a roller bucket, but whatever the flow that is coming in as supercritical, it would shoot off the bucket. So it's just shooting off the bucket and then falling in. So instead of allowing it to go directly onto the bed, you're just allowing the flow to shoot off. And here it is going to lose energy with the turbulence. So this is called ski jump bucket. And then we also have chute blocks. So let's say that is the spillway. Then what we do is to provide blocks. Or these are called friction blocks or chute blocks. So if you provide these blocks, then whatever the flow is coming in is facing an obstruction. So by hitting these obstructions, then you're increasing the friction. And so you're reducing the energy of the flow. So these will be provided on aprons or on a concrete surface, not on the soil. So making use of these chute blocks or friction blocks, you can also dissipate the energy. Now, these are the different types of energy dissipation mechanisms on spillways. And the last topic we are going to see is spillway gates. So in terms of spillway gates, one, there could be vertical gates, and two, there could be a radial gate. And you can see both of them here. So here you see it looks like a radial gate. So this is what it looks like, the radial gate. So it is curved. So this is not vertical. So this is curved. And to discharge the water, you would raise the radial gate and then discharge the water. Whereas the vertical gate would be simply vertical in section. So if you're seeing it from the side, it would just look like a vertical face. So these are the two types of spillway gates. Now, keeping in view the time constraints, because the classes have been preponed and the exams have been preponed, I have not gone in depth about the design of the spillways or the design of the gates, but we will see one example on the design of spillways on Monday. So this would cover the syllabus for the exam, including the example on Monday. And I have uploaded the tutorial solutions for all the questions except question number 12, which we will do on Monday. So on this topic so far, do we have any questions?
No, sir.
Excuse me, sir.
Yes.
Sir, in design of dams, we have to follow all the steps. Like there are many steps in designing of the dam.
So for the design of dams, in the questions you would be asked to calculate specific forces. Like I might ask you to calculate hydrostatic uplift and earthquake force, or a combination of 2 or 3 forces, not all of them. And based on the selected forces, you may have to do the stability.
Yes, sir.
Yeah. So the syllabus, so for the exam, if you just follow the lecture notes and the tutorial solutions, then it should be fine. So it would not, I would not ask anything beyond that. And in spillways, we will see a design example on Monday, and the spillway portion would include the theory today and the example on Monday. So this is the last theory lecture, but I also wanted to let you know, since all of you are busy in finding jobs or planning further steps. So if you need any help from me for higher studies or anything else, you can contact me and I can try to provide any support that I can. So if there are no questions for today, then we'll meet on Monday at 11 o'clock, the usual time.
Thank you, sir.
All right. Thank you and all the best for the exams as well. See you all
Thank
on
you, sir.
Monday. Bye.